from this guy we're going to hear about Halley's Comet. I will start the YouTube stream. So all that remains is to introduce our headline speaker. I'm here with Dr. Stephanie Monty, who's going to be telling us all about nucleosynthesis, the story of us as told by star stuff. So a big hand for Stephanie.
I should be off mute, yes, okay. Thank you very much, Matt, and thank you all for coming despite the clouds. I appreciate it. And it's going to be nice to talk in the dark. There's no point in dressing up, but that's okay. So I wanted to talk to you about an area of galactic archaeology that I really love. It's nucleosynthesis. Not only is it a mouthful, it's a massive field, but I think it's really special because it has a very direct connection to us as human beings and everything that we're made of. So I want to sort of take you through tonight where the elements in the universe are formed, what sites they're formed in, and a little bit about those objects themselves. So nucleosynthesis, by definition, is the formation of atoms that are more complex than hydrogen. There are two areas of nucleosynthesis. There's Big Bang nucleosynthesis, so that's hydrogen, helium, and lithium, the lighter elements. And then there's stellar nucleosynthesis. So this is everything heavier than boron, and that's what I want to talk to you about tonight because this is sort of the area of expertise I have. So it is true that we're all made of star stuff, just different kinds of stars at different points in the universe and by different means. So this is sort of a connection to Cambridge. There's an incredible paper that was published in 1957 that we affectionately called the B²FH paper. And so this is really the beginning of the field of nucleosynthesis, and it was written entirely by 4 astronomers while they were at Cambridge. So this is a beast of a paper. It's 108 pages, which I'll get to in a second. But so the lead authors, Margaret Burbidge and her husband, Geoffrey Burbidge, were both observational astronomers, so they studied the spectra of stars. William Fowler did laboratory experiments to investigate synthesis methods and formulas. And then Hoyle was the idea man. So Fred Hoyle actually was the first person to propose that the heavy elements have to be formed in stars. And so together they wrote this incredible paper. And Fowler went on to win the 1983 Nobel Prize. Unfortunately, his co-authors were left off, and this was shocking to him as well as everyone else. So Margaret Burbidge, I just want to mention briefly because she's quite an inspirational figure to all astronomers, but especially to myself. So there she is on the left in the middle, with her husband on the right, Geoffrey, and then Fowler on the right, and her husband on which is that? Her right. Sorry. And then on the other image, there she is with her spectra. So she observed the stars and deduced from the spectra what elements were present and in what amounts. So she did this despite being denied access to the majority of telescopes that she applied for time at. And this was because women were not allowed on the site at the time. She was also denied fellowships because of her gender. She was the first woman director of the Royal Greenwich Observatory, and she was also nominated at the same time as the next Astronomer Royal. Unfortunately, she was not elected. And since its inception in 1675, there has never been a woman as an Astronomer Royal. So many of you will be familiar with the periodic table of elements, but you probably would have seen it from the chemistry point of view, where we group elements based off of different basically into alkaline earth metals and transitional metals, and etc. The nucleosynthetic point of view is to instead group the elements by where they're formed. So we have this beautiful graphic produced by Jennifer Johnson, and I'm telling you where each of the elements is formed, by what method, and generally you can see that there's a bit of a trend. So as we go up the table, different sources produce each of the elements. So as I said, I won't talk about Big Bang nucleosynthesis. That's not my area of expertise. So I'm going to focus on these 4 groups instead. So neutron stars, low mass stars, massive stars, and white dwarfs. So all stars are powered by nuclear fusion. This is also how the elements are formed. And nuclear fusion is essential for a star to support itself against the crushing effects of gravity. So this is how the star generates energy. And it really comes back to this very simple equation, but very powerful equation. And this relates mass to energy. So this is a very simple fusion reaction that occurs in stars. This is the end of what we call the proton-proton chain. And this sort of is the quintessential reaction that occurs in stars when they're first formed. So if you can complete the proton-proton chain, you're now deemed a star, and congratulations, you have entered the universe. So this is the very end of the proton-proton chain when we're fusing two isotopes of helium, in the end to get one stable atom of helium, two hydrogen atoms, and energy. And so you'll see here that you're converting the mass into energy. This is how the stars support themselves, and this is how the elements are formed. So this is just a figure of that process, the PP chain, and then in the end, you'll see the equation that I showed for you. That's the result here. So each of the elements, as I said, they're produced in these stars. They're produced generally, what governs the production is the mass of the object. So all the stars are born on the left, and then they progress through their life to the right. And as you go up in the diagram, that's increasing in stellar mass. So if you're a little brown dwarf, born a low mass object, you're going to live for a very long time, and you're not going to do very much exciting stuff. From an astronomer's perspective. And then if you're a massive star right at the top, of course, you have a very violent and short life. So I'll be focusing on the stuff right in the middle. So I'll be talking about the low mass stars, stars like our sun, sort of intermediate mass stars that become core collapse supernovae, and then the really massive stars in the range of about 30 to 150 solar masses that end their lives as neutron stars and black holes. So I'm going to start with the dying low mass stars. So these are stars that are approximately the same mass as our sun, and there we go. And they're really fascinating objects. Despite being deemed average by most stellar astronomers, stars of this mass are necessary for creating carbon-12. So that's, as far as we know, an isotope of carbon that's essential for all organic life. And this happens in stars just like our sun. And zirconium I put on here because I thought zirconium was kind of neat. I didn't know that it was actually a very critical ingredient early on in initial preliminary kidney dialysis systems. And these are both formed inside of stars like our sun. So here are some other elements that are attributed to these stars. So you can see anything colored yellow, strontium, yttrium, carbon, nitrogen, a whole bunch of exotic ones that I don't remember the name of. And so how does this happen? Right, so it happens through fusion, like I've said, and to fuse heavy elements, you need a lot of temperature and pressure. So as you go inwards into the star, naturally the temperature rises, as does the pressure, and so you start to fuse heavier elements. So inside of a star just like our sun, at the end of its life, you'll see that in the very center, you've got a lot of carbon and oxygen, and then you have some helium burning in order to support the star from collapsing. So only about 1% of their lives is spent in this phase. So our sun is about halfway through its life and nowhere near this phase in its life. But this is really incredible considering they only spent 1% of their life, but obviously we have a lot of carbon in the universe in high abundances. And so this is the beginning of the end for stars that are about 0.5 to 8 times the mass of the sun. And so this is a beautiful image of one of these stars in its final throes of life or death. And this is, so all of those elements that are produced within the star enter the universe, the interstellar medium as we call it, through very high velocity winds. So these winds sort of blow all of this material off of the star, and then they create these really beautiful images. This is an ALMA image of stellar winds. And this particular object has a companion that's sort of circling the star and cutting through the wind, creating this very beautiful rosette. Here are some other rosettes as well. So these are all stars that are enriching the universe in carbon, nitrogen, oxygen, and everything essential for life. So then we'll step through to something slightly more exciting, perhaps. So these are type 1a supernovae. This is another evolutionary step for stars that are potentially the same mass as the sun, but it's a more violent end for them. And type 1As are responsible for cobalt-60, which again I thought was really neat. It's an isotope of cobalt that was used in early radiotherapy treatments. And they're also responsible for an element that's critical to this. So I wonder if anybody recognizes this organic molecule. By chance? Yeah? Is it a protein? It's, I don't think it's a protein, but it's a protein structure. It's sort of structured the way that a protein would be presented, right? Yeah. You're going to correct me in a second, I'm sure.
Hemoglobin?
It's hemoglobin, exactly, yeah. So right at the center of hemoglobin is an iron atom. And of course, that's basically, it's critical for the transportation of oxygen within our bodies. So supernovae 1a in recent times have created the majority of iron we find in the universe. What's incredible to me is that there's only 3 to 4 grams in your body, and it's less than 0.0001% of your mass, and yet it's critical to your survival. So the next, so I thought I'd list some more elements for you that we have supernovae 1a to thank, including nickel and zinc, as well as others. And so how do these occur? So after our dying low-mass stars expel all their winds, their atmosphere off of themselves, what's left is the bare core of the star. So in this image, you're seeing a planetary nebula where all the beautiful blue you see around, that's the sort of atmosphere of the star that's been blown off and away from the core. And so what's really neat is that they go at different velocities, so you get a shock front. So the inner pink region is moving really fast, and the outer region is a lot slower, so you get this nice delineation. And the core of the star that's left behind is called a white dwarf, and remember that's just carbon and oxygen. And here are some beautiful planetary nebulae just to look at. And again, you can see there's different shapes and geometry, and that all can tell you about the system and whether the object has a companion, whether it's actively, we use the term accreting material, so gaining mass. And this guy, the Ring Nebula, you can actually see from the northern hemisphere in November. So that's something that you could, if you have a backyard telescope, try to look at. You can also use binoculars. So what happens with 1As and how do they create all these elements? Well, there's 2 predictions for how 1As go off. There's a single degenerate scenario and a double degenerate, we call it. So on the right here, you'll see the white dwarf has a companion, and its gravitational pull is stripping mass off the companion and starting to pile it up on top of that core. In the double degenerate scenario, you have 2 white dwarfs circling each other, and given enough time and certain geometry, they'll infall to each other and coalesce. So Chandrasekhar discovered this incredible limit, which is named in his honor, the Chandrasekhar limit, where essentially if a white dwarf gains enough mass that it surpasses 1.4 times the mass of the sun, it becomes a 1A supernovae, which is a thermonuclear explosion and one of the most powerful energetic events in the universe. So in these 1A supernovae, elements are formed that require a lot of energy. So I'm showing you here one of the sort of common diagrams we use in nuclear physics. So on the left is energy to produce the atom, and on the bottom is, the y-axis, and the bottom is mass number. So you need a lot of energy to create heavier atoms. So you need very energetic environments. Elements up to iron and just beyond are synthesized inside the explosion. Here you have fusion. So in this case, you can generate energy by fusing elements to the left of this line. And in this case, you can generate energy by splitting elements. But you don't fuse elements beyond iron. So stars cannot fuse elements beyond iron. So the next one I want to talk to you about are core collapse supernovae. So these are another incredibly energetic event that happens in the universe. And these are responsible for another thing that I thought I might ask the audience, whether you recognize this image. Any familiarity? Donuts, maybe? It's another biological thing. So this is a positron emission tomography of the heart, which I thought was really neat. So this is imaging the heart, and it's using an isotope of rubidium called rubidium-82 that's fused inside of core collapse, it is fused inside of core collapse supernovae, created in the events, rather. And when rubidium-82 decays, so it experiences nuclear fission, then you releases a positron, and this is actually what's being imaged, which I thought was very neat. And gallium is another fun element, has a melting point of 30 degrees Celsius, so it melts in your hands. And then you pour it, and it reforms. I think it's quite toxic, so don't do that. So, and here are some really fun elements, again, created by these core collapse supernovae. So you notice oxygen is primarily dominated by this, magnesium, sodium, potassium, and then a lot of really fun elements as you go up. So in this case, once again, you're fusing elements, and because in this case you have more mass, you can drive the temperature up higher in the core, and you can continue to fuse elements until you reach iron. And remember from the graph I showed you that iron is really the tipping point, and no longer can the star support itself because it doesn't gain energy by fusing iron. It loses energy. And when it loses energy, it loses the battle against gravity, and it eventually starts to collapse. So in this case, you're seeing the very end of the star. And so those outer layers you see, they basically just all start to fall inwards onto the star, and it's a runaway reaction that ultimately leads to the star exploding. And it looks like a gumball. I don't know if you have these in the UK, probably not. They're a health and safety hazard, but we had them in Canada. Okay, so I wanted to show you this video of this because it's quite beautiful. This is the creation of the Crab Nebula. So it's, of course you don't see the interior, but you do see just the beautiful explosion. And the result is a Crab Nebula, which went off in 1054 AD. And so it's recorded by ancient Chinese astronomers, was the brightest object in the sky for a long time, was visible during the day for a month. So this was one of the first recorded events we had, astronomical observations. It's really loud. Okay, there we go. And here it is, a composite image. So this is HST as well as Chandra. So this is optical and X-ray. And you're seeing it, the different colors represent different wavelengths. But what's really neat is right at the center of the Crab Nebula is a really fun object, a really bizarre object. And it's, you can see it surrounded here by a bunch of material that's quite hot. So it's emitting an X-rays. And this is a superheated material that's surrounding the central neutron star. So there's a neutron star right at the center of the Crab Nebula, and it's a pulsar. So it's rapidly rotating and doing a lot of exciting stuff. I've just noted down the axis of rotation. So it rotates around the line that I've noted. And then you have some jets down below, right there. So neutron stars are our last nucleosynthetic site, right there, and then also black holes. So these guys are really responsible for creating all of the heavy elements in the periodic table, as well as some really exotic elements. So I just noted down some. So iridium, this was a really neat one. This was created in neutron star mergers, and it's the main point of evidence for the Alvarez hypothesis, which is, anybody familiar with that one? Any archaeologists in the room? Paleontologists? No. So I didn't know this till recently. This is essentially the one of the lines of evidence that the dinosaurs ended with a massive, by a massive catastrophic event in the form of an asteroid hitting the Earth, right? So they found iridium is primarily found in asteroids, and they found a nice thick layer of it, I guess, between the transition of paleological eras in the place that they believe the the asteroid struck. And then it's also, these are sites also responsible for polonium and radium, which are both discovered by Marie Curie. And so here's some more exciting elements. There are two elements you notice that are in gray. These are technetium and polonium, perhaps. Not polonium, it can't be polonium. Technetium at least, number 43. So that's an element that's not synthesized in stars and can only be synthesized in labs, which I think is pretty interesting. So neutron stars are interesting objects for a lot of different reasons, but they are the densest objects in the universe. So I've put here an image to show you the scale of a neutron star, which is about tens to hundreds of kilometers across, and it's hovering just above Vancouver. So that's a place close to my heart. And neutron stars, yeah, they're quite interesting. So you'll hear in astronomy many different analogies or ways to sort of talk about how dense neutron stars are. So you see this one quite commonly. 1 teaspoon weighs the same as Mount Everest. Same density as an atomic nucleus, so it's just a giant nucleus, which I think is quite cute. And then this one I thought was interesting. So it's equivalent to 250 million African elephants squeezed into the volume of a sugar cube. So these are essentially, once again, you're looking at the core of a star, but you're looking at the core of these massive stars that end their lives as core collapse supernovae. But they're not really typical stars in the common sense. They're composed entirely of neutrons. What's at the center is not well known, whether it's liquid neutrons or not. So here I just wanted to show you how the neutron stars themselves merge and release these heavy elements into the universe, or synthesize these heavy elements. So this one's quite cute as well. So here's 2 neutron stars. They probably were a binary star system initially. And then here they are emitting gravitational waves. So as they interact with space-time, they release gravitational waves. And these were measured very recently with the LIGO interferometer. And of course, were one of the predictions of general relativity, incredibly bright. So when they emerge and die, they create a kilonova, which is, or a hypernova, which is one of the most energetic events in the universe, even more energetic than a 1A supernovae. So ultimately, now that you know where all the elements come from, how do we use them in terms of galactic archaeology, and how do we measure them? So this is what Margaret Burbage would have done very early on. She looked at stellar spectra, and if you see the black lines, these are absorption features. So these are, each of these black lines is caused by a given element absorbing a photon of light, so some energy. And then where the black line occurs and how strong the depth of that line, if you know the temperature of the star, can tell you how much of that element is present. And so each of those sites I showed you have different time scales. Some happen very quickly in the scale of the universe, and some take longer to occur. For instance, core collapse happened very early, about 200 megayears after the Big Bang, and then it takes much longer for 1As to happen. So each of these lines, again, is related to a different element. A very popular element that we measure in galactic archaeology is iron. So the sun happens to have a lot of iron, and I think this is perhaps why we've chosen it as our element, even though iron is attributed to both 1A supernovae and core collapse. But we use it as a measure of age. So it helps us date and say which generation a star was born in. So was it born very early on in the universe or more recently? So the oldest stars have about 1/1,000,000th the amount of iron that the sun has, so which is pretty incredible. And the very first stars that are theorized to exist, but we have not found one yet, have no iron at all. So it may be that we can never find them because they would have been very massive and ended their lives very quickly, which is pretty incredible. And so I'll show you in the end the composition of our sun, which is a fairly average star. Maybe that's just our point of reference, but it's become an average star. And so we can see primarily it's hydrogen, even though it's a relatively young star. It's got, in the scheme of the universe, it's mostly hydrogen still, helium, neon, sulfur, and a little bit of everything else. And there's the composition of the human body. So of course we're primarily oxygen because we're mostly water. And this is composition by mass. So I'll just take you through to wrap up the origin of, again, each of these elements that are inside of your body. So carbon and nitrogen, primarily low mass dying stars like the sun. So again, they have these very strong winds that push out these elements that they synthesize inside. Oxygen, calcium, phosphorus, all of those fun isses, they were all created inside of core collapse supernovae. So these happened very early on in the universe from massive stars ending their lives. And then a little bit of calcium, sulfur, and everything else we attribute to type 1A supernovae and neutron star mergers. So even iodine, which I think is one of the heaviest elements that is necessary for the body to function, that's created inside of type 1As, I believe, which is very neat. So I'll just leave that up for you so you can see the composition of your star stuff, I suppose. All right, thank you.
Okay, the lights are going on, brace yourself.
Yeah.
There's no dim light option, I'm afraid. Wonderful, Stephanie, that was fantastic. Thank you so much. Do we have any questions for our speaker? Yes.
What's the lifetime of the low mass stars that make all the carbon?
Yeah, I think it's on the order of 10 billion years.
So does that mean you couldn't have carbon life before 3 billion years ago?
Yeah, that's right. Yeah, I think that's a fair...
What does that tell us?
Well, it's an interesting thought experiment, I suppose. Maybe that you need, that in fact there's another basis for organic life. It doesn't necessarily have to be carbon-based.
Does the abundance of each, does the abundance of matter or each element within a star change what element it's going to produce?
Yeah, absolutely. Yeah. So we call it a metallicity-dependent yield. So depending on how much iron you have, so when you were born in the grand timeline of the universe, can tell you how much other elements you produce, for instance. Yeah. So there definitely is a dependence on your initial composition as well. Yeah.
Does that tell us what generation of stars?
Yes. Yeah.
So are for example, blue stars a more advanced generation than yellow stars, or it doesn't?
So the color of the star typically just tells you the temperature. So in that case, you're not necessarily learning about when it was born, but what stage in its own life it's at. Yeah.
There's a question there, you're patiently waiting.
The sun, when do you think it might explode?
Oh, the sun. So the sun will end its life in approximately 5 billion years is the estimate. So it will become a red giant star, and then it will start to spew out into the universe all of the carbon and nitrogen it's created during its lifetime. So it will go on to enrich the universe and stuff that is needed to continue to make life, which I think is neat. Yeah.
But it won't explode, right?
No, it won't explode. You're right. Yes, no, it won't explode. It will just end its life it'll have those strong winds, and then it'll be a beautiful planetary nebula like the objects I showed you. Yeah.
Amazing. Yes.
How big is an average supernova?
How big is an average supernova? So I think I need to have an estimate of the amount of energy inside of one of those events. I can't give you, I should have a ballpark. Matt, do you have a ballpark idea?
I don't know if I do.
Yeah.
Is it sort of like 10 to the 50 ergs or something?
Yeah,
Like,
yeah,
is that
10 to the,
ballpark right?
yeah, I think so. So it's,
I'm Googling it.
yeah. Thank God for the internet. Yeah. Well, I guess the only thing I could, an easy sort of reference is to think of that Crab nebula that I showed you, that when it went off as a core collapse supernovae, you could visible during the day for a month. So that tells you, and it was as bright as Venus.
Okay, so here we go. So it's...
Yeah.
The numbers get so big, it's quite hard to say. So 1 followed by 44 zeros joules.
Is the amount of energy released.
Which is, it's about the energy that the sun will release in its whole
lifetime.
life.
Yeah.
In one go.
Yeah. Pretty incredible. Yes?
You mentioned that the very first stars, theoretical ones that had no iron in them, would have been really big. Is that because they're older or because they have no iron in them?
Yeah, so that's a good question. So the first stars are theorized to be very massive because they have no iron. So it's stars actually, you think that it's sort of a challenge to get the engine to turn on, to this nuclear fusion to happen, but the real challenge is to keep the engine from overloading. So it's sort of like it needs a way to keep the thing intact. So we call them cooling mechanisms, a way to keep it to fuse in a sort of steady state rather than just fusing all its fuel very quickly and burning bright and ending its life. So the very first stars didn't have a lot of that cooling mechanisms available because there was no other elements around to help with that. So yeah, but it's very much the realm of simulations. So it's still trying to get a handle on how massive these stars would have been. If there are any, most of the stars we look for, or the evidence of the first stars we look for, is the generation that was born just after. Yeah, so they are hanging around the Milky Way, and there's, I think, about maybe 20 or 30 of them found at this point. Yeah.
There's loads of questions at the back there. How about we start with how the difference between you?
Why doesn't hydrogen have one of those boxes around it?
Oh, yeah, that's a good point. So hydrogen is created during the Big Bang. So it was created about less than 20 seconds after the Big Bang. It was so it happened through the process of Big Bang nucleosynthesis, which is neat because it means that the hydrogen in your body is at least 13.7 billion years old. Very cool, huh?
Yeah.
How long ago do you think the sun was made?
So I think our estimates are somewhere between 4.5 to 5 billion years ago is the age of the sun. That's sort of going off of the current evolutionary state we think it's in and how long we think it should live for. So it's a bit of a guessing game, but we've got at least 5 billion years left, I would say safely. Yeah.
So many questions, I like it, yes.
So stars that do have iron in it, how much iron do they have?
Yeah, that's so. Well, the sun has about 1 million times more iron than the very earliest stars, but there are stars that have more iron than the sun, so they were born even more recently, and they're all around the Milky Way, but most of them live in the Milky Way disk. So when you look up in the night and you see the big Milky Way overhead, those are all stars with a lot of iron, predominantly. Yeah.
But how much iron actually is in the sun, like as a percentage?
As a percentage,
You don't have to
yeah.
be on the spot,
No. I actually have the percentage of the. So iron is about 0.003, the number content of the sun. So not by mass, but by number of atoms. So just a tiny amount, tiny fraction of iron in the sun, which tells you how little iron must have been in the very first stars. Yeah.
Cool. How about we do, there's 2 questions there, and then at the top, and then we have a break. Yeah, so right to the back.
I've got 2.
Can you do your favourite one? Pick your best question.
You said 2 stars merge into one in a video.
Mm-hmm.
Can 3 or more merge into one?
Oh yeah. Yes, they definitely can. So multi-star systems do occur. They have to happen in environments that are quite dense. So we think it happens most often, or most likely would happen in the center of a star cluster. So if you've ever seen a globular cluster in the sky, right in the center of those, we think multiple stars can merge, but probably very early on in the cluster's life. But yeah, that's a good question.
Cool, and then we'll have one last question, but I think, do you mind staying around and answering some questions as we go out to a break? So one last question for now before the tea break, but Stephanie's going to stay around and answering questions. There was an arm around there somewhere. It's gone now.
Is it possible that life forms could form on other planets?
Oh, that's a good question, and a hard question to answer. Do life forms, so I think, yeah, I mean, this was brought up early on, right, whether all life is carbon-based or not. I think if we're able to find that, that life can form by other means, then I think there's maybe no reason that life couldn't form on planets that we consider inhospitable. But even the debate about that there might be organic molecules in the atmosphere of Venus, those are life forms, right? Forming in something that we would consider, you know, a complete opposite kind of environment you need for life. So I think that's absolutely no reason why life couldn't form on other planets. Yeah, but it's not my realm of expertise. I'll put my foot in the mouth later. So.
Amazing, cool. So I think, yeah, so time for a quick tea break and then back to hear all about Halley's Comet. Stephanie will be around and answer questions for the hands that didn't get answered, but before that, can we thank our speaker again?